but have high magnetic permeability and high resistivity. So they are preferred for such. And since okay, so ferrite-based modulators are devices that use ferrite materials to control microwave signal characteristics. We can control characteristics such as amplitude, frequency, and phase. This is the different types of modulators that we know. So ferrites exhibit non-reciprocal properties, meaning they can transmit signals depending on the direction of propagation. This we knew from the last presentations. So ferrite-based modulators are widely used modulator types. This is because of their high power, high isolation, and the ability to hold large power levels, making them suitable for applications mostly in military and aerospace industries. Their principle of operation, they rely on the gyromagnetic properties of ferrites. The gyromagnetic effect is when ferrite, when exposed to a magnetic field, the dipoles precess around a magnetic field. So this changes the permeability of the material, affecting how microwave signals propagate. And also in the principle, you have also non-reciprocity, where ferrites allow microwave to pass in one direction with different characteristics than in the opposite direction. This is critical for preventing interference. We also have magnetic biasing in the principle of operation, where ferrite modulators require magnetic biased field, which often rely on a permanent magnet or an electromagnet to influence the ferrite's permeability by changing the strength and orientation of magnetic field. To the next slide. Then we have the different types of ferrite modulators, ferrite-based modulator types. We have seen that they affect the phase, amplitude, and frequency. So here we have ferrite phase modulators, which are devices that vary the phase of the microwave signal by altering the magnetic field across the ferrite. But their response is the usual phase modulation that we know, as you can see from the picture. So by changing the phase, these modulators are essential in systems where the phase is crucial, especially in phase array antennas. The next type of modulation we have is amplitude modulation, where these modulators control the amplitude of the signal. When the magnetic field is applied on the ferrite, it changes the impedance, allowing for controlled variation in signal's amplitude. This is the usual amplitude modulation that we've learned, and you can see the the response of the modulated wave and the carrier. The next form of modulation is the frequency modulation, where ferrite frequency modulators. In this modulation, the frequency of the microwave is modulated such that the magnetic properties of the ferrite material is subjected to varying magnetic field. They cause changes in the resonance frequency, which modifies the signal's frequency. We can see the response of the frequency in the different types of signal here. It is the usual frequency modulation, but based on the ferrites. In their design, we have certain design specifications, such as the magnetic field strength. The applied magnetic bias must be precisely controlled to achieve the desired modulation effect. That is in magnetic biasing. The next we have frequency range. Ferrite materials they typically are optimized for a specific range, so they tend to work in a specific frequency range. Then they are temperature sensitive, such that ferrites are sensitive to temperature variations, which can alter their magnetic properties, affecting their performance. For high stability ferrite materials or compensating circuitry, they are often used in temperature sensitive applications. This means that it can be a limitation in their use. In power handling, we see that ferrites are chosen for their high power handling capabilities, which makes them suitable for applications such as radar and satellites. In the next, we have applications for ferrite-based modulators, radar systems, where ferrite are essential in radar for controlling signal timing and phase. This is because they can handle large power. In satellite communication, ferrite-based modulators adjust the phase and amplitude to maintain the stable and clear communication. They're also used in microwave communication links, where they help stabilize the modulated signal for long distance transmission, especially requiring non-reciprocal signal paths like in telecommunication. The advantages of ferrite-based modulators is that they have high efficiency, which minimizes the signal loss. They are also compact and durable, which enable development of compact and durable devices, meaning in their size, so they can be fitted in small devices. Their non-reciprocal behavior, which allows for effective one-way signal control, reducing the interference. In limitations of using these types of modulators, you have temperature sensitivity, where their performance may degrade at extreme temperatures. So this affects the locations where we use these modulators. The, we also have magnetic biasing. It is complicated to achieve the magnetic biasing for the ferrites. It complicates the design. We also have the material cost. For high quality ferrite materials, they can be very expensive. So there are also future trends. The future trends in ferrite-based modulators will be to achieve. Okay, I don't know where the slide is, but it will be to achieve ferrite materials that are optimized to operate in extreme temperatures. So that was my presentation. Welcome the next presentation.
Yes, hello, good morning. I'll be presenting on ferrite devices. Give me a moment to share the screen. Stephen, can you confirm that you can see my screen?
I can see your screen.
Okay. So mine will be on the gyrator. I'll discuss on the mode of construction, the principle of operation, and its application areas. And I'll first review the Faraday's rotation, whereby we are saying you have a linearly polarized wave that is in the x-axis, E naught, and then I hope you can see that page that I am on.
Yes.
And then, okay, and then you have the direction of wave propagation that is in the z direction, and what you are saying, you also apply a magnetic field, BO, parallel to the direction of that wave. What you will notice, suppose the gyrator starts from here, goes all the way. So as the wave is propagating from z is equals to 0 to z is equals to L, what you'll notice is that the plane of polarization will keep on rotating. The plane of polarization, we mean that the direction in which the electric field is rotating. So you'll find that a distance closer to z is equals to 0 will have a phi 1. Then at a certain distance, it will increase to phi 2, and it will go all the way to z is equals to L at phi something. Then what you will notice is when now the direction of wave propagation is reversed, the rotation continues in the same direction, whereby now angle will keep increasing, maybe from theta 3 all the way to theta 4 to somewhere now you are returning to at z is equals to 0 here, where you find that now the angle of rotation will be 2 theta. This principle will be used in our gyrator, whereby you will find you'll give it a signal at point 1, and then at point 180 degrees, we will see that in a bit. So I'll discuss its mode of construction. Its mode of construction, you'll see is at port 1 is here, you'll have a rectangular waveguide. Then at the center here, you'll have a circular waveguide. And then at port 2, you'll have again a rectangular waveguide. Then you'll find now we are transitioning from rectangular waveguide to circular waveguide via a twist here. Here is a twist that will give us a transition. And then here we'll have a ferrite device. In our case, is the gyrator. Then from there, we will then transition back to the rectangular waveguide. Come first to the gyrator here. This one here. It's do I say a cross section or what? Is on the right side here. You'll see that we are applying a constant DC static magnetic field. You can see them here. And then we have a ferrite material here, this one here, that is surrounded by a foam or a polyfoam. So several parts. One, the polyfoam will provide a mechanical support and stability so that this ferrite material doesn't move, doesn't keep rotating. because you know when you rotate, you might cause some impedance matching, which will result to reflections that gives a power loss to the wave. It also, we have said that it reduces the signal reflections, that is by holding the ferrite family, and also it helps in thermal insulation, whereby now you may find that when the ferrite material is has a raised temperature, it will have some behaviors whereby now it will result to some reflections. So there we have discussed about the gyrator. Now we can discuss about the twist now here. Here is a twist. It is made such that it will have a minimum, or if no reflection, it will have minimum reflection as we move from one mode to another. Because now here in the rectangular waveguide, we have a TE10. Now in the circular waveguide, we'll have a TE11 mode. Then you'll have you will see on the gyrator that it is
You can't see your presentation.
Hello. You can't see my presentation?
Yes.
Yes. Oh, sorry for that. Now you can see my presentation, right?
Yes.
Okay. We are on the mode of construction. Sorry. Let me embark on the gyrate. The gyrate is tempered on both sides. These are the tempering we are talking about. Again, is for the same purpose, to reduce the reflections. Because now you will see here, now we are at a boundary here, and one of the causes of reflection of a wave is a change in boundary. Now you need to transition smoothly and gradually from an air here to the ferrite material here. That is why we need to temper it to reduce the reflection. So I think I've talked all about that. The polyform. Yeah, now we can go on the mode of operation. Before we define now what a gyrator is, we need to understand how the angles are coming about. So at port 1, here is port 1 here. We feed in a signal or a wave TE10. It is vertically polarized in the X direction, the electric field. So it comes, find the twist here. When it crosses the twist, it is rotated anti-clockwise by 90 degrees. 90 degrees anti-clockwise. So at a point before it enters the ferrite, it is already at 90 degrees out of phase from port 1. Then it enters into the ferrite device, in our case the gyrator. The gyrator rotates it further anti-clockwise with a 90 degrees shift. Now it comes here at 180 degrees. Here there is a smooth transition, not to alter any phase of this signal as it leaves this point here. So you'll find at port 2, you'll have our signal now, it is 180 degrees out of phase. Suppose now you feed a signal into port 2. Let's see the behavior at port 1. So you'll have a T10 at port 2 here. It is polarized in the X direction. Therefore, just before it emits the ferrite device, it is perpendicular, that is in the X direction. But now it enters into the gyrator, where it receives. Remember, we said that the direction of the wave propagation doesn't matter. That is, the rotation will continue just as it was in the forward direction. So in the reverse direction, we expect a rotation in the same direction. So it will be 90 degrees anti-clockwise. So now we are at a point here now where we have our E at 90 degrees anti-clockwise. We find a twist here now. Here is our twist again. In this case, the direction of wave propagation is opposite to the forward, and therefore it will counter the effect of this 90 degrees rotation at the ferrite. So what you will find, what you'll find is now, instead of rotating further by 90 degrees anti-clockwise, it will be counter effected back to the 0 degree that was initially here. So what you find at port 1 is our wave is again vertical. Therefore, you have a phase shift from port 1. Phase shift is from port 1 to port 2. And then that is pi radians phase shift, and our 180 degrees phase shift. Then from port 2 to port 1, we have 0 degrees, 0 radians phase shift. That one we've seen. Therefore, now we can clearly define the gyrator here. But a gyrator is a two-port non-reciprocal device made from ferrites and has a relative phase difference of 180 degrees from port 1 to port 2. Then it has a 0 degrees phase shift from 2 to 1. That one we've seen. Then we know that ferrites are made from non-metallic magnetic materials. That is now iron oxide, you combine it with another metal, maybe a zinc and nickel. And that's the mode of operation. Then I'll go ahead and let me see, and discuss the scattering parameters of the gyrator. We know the scattering parameters of an n-port device is n by n matrix. So this is a two-port device. It will have a 2 by 2 matrix, where S11 is the reflection coefficient of port 1. So you feed a signal at port 1, then what amount does it reflect on the same port? The same case for port 2, you feed a signal there, what amount does it reflect back? Then you have a signal that is fed at port 1, then what amount does it go to port 2? The same case here, you feed a signal at port 2, and then you see the behavior at port 1. in our case, we will assume that the gyrator is an ideal gyrator, so that S11 and S22, they are 0, so no reflection. So this becomes 0 and 0. So our matrix now becomes 0, S12, S21, and S22. Sorry, this is 0 as well. Then we are saying you feed a signal at port 2, you'll find that this electric wave has not changed in the plane of polarization. So you will find that it is 1. It is 1. Then you feed a signal at port 1. What is the behavior at port 2? It will be rotated by 180 degrees. Therefore, when you do this, you'll find it is -1. So this becomes -1. So our matrix now becomes this one here, 0, 0, 1, and -1, which definitely describe the non-reciprocal properties of the gyrator. We go to the application areas when it is used in the isolator to enable a one-way signal flow, whereby now protecting sensitive components by blocking reverse signals with a 180 degrees phase shift. The other one, it is used in circulators to serve as a building blocks for enabling a unidirectional flow among multiple spots by directing signals in one-way loop. It is also used in phase shifters, where now you feed a signal in one port, it will be shifted in the other port. It is also used in impedance inverters, enhancing filter performance and matching high frequency circuits. And that's the end of my presentation. Thank you. I was the last member to present, so Stephen, you can take over from there.
Okay, so if we're done with the presentations, I think we can call it a day and end the class here. And if the lecturer was present, we were to go through some equations, but she's not going to be in today. So yeah, I'm just prepared to submit the tutorial next week on Tuesday. So we'll have a class tomorrow, unless Dr. Akon communicates otherwise. I'll let you know since we're done with the presentations.